You're on.
All right. Thank you everyone for coming and giving us 15 minutes of your time to listen to our project presentation here. Nothing fancy with a name, Smart Connect 4. We're hoping it's smart, some bit of intelligence. Myself, Harrison, Hunter, Eric are the team of 3 working on this. We're going with the name, the D team. Eric? Just a basic explanation of Connect 4 and how to play. The goal is for you to get 4 chips in a row, horizontal, vertical, diagonal, either way, and also preventing your opponent from doing that first. Pretty straightforward. So our problem here, and our goal, is to create a solution for lonely people who don't have someone to play with them. So trying to create an intelligent robot that will play the chip and also make the decision of where that chip's going to be played with minimal input besides, loading the hopper or the magazine with chips and then hitting the start switch. You shouldn't be having any other input after hitting go until the game is over.
Our solution was to have a gravity-fed magazine that's vertical, that goes down into a slide gate, that drops the chips down into a slide gate system by spinning a motor with the little arm on it that knocks the chips out of the clip. And then in the slide gate, we'll have the gate will have a slide that goes back and forth along the top of the board that allows us to drop the pieces in any of the rows, and there will be sensors along. There's going to be 7 breakbeat sensors across the top in each of those holes that when the chip passes through it, trigger an interrupt and store the chip locations in our array. And our software strategies, we're each going to work. Harrison's going to do the diagonal, I'm going to do the horizontal, and Eric's going to do the vertical, and we're going to focus. We have like a priority list where the first thing it checks is if somebody won. Second, it checks 3 in a row if we can win. Third, it checks 3 human places in a row to block. Then it goes 2 for us and 2 for humans, and so on.
Yep. It does that after every human play. Yeah.
And this is what Hunter was just talking about.
Yeah.
This is the magazine, and it's going to drop a chip when it's time to, and then it drops the chip after this slide gate moves to the appropriate position of where we want it to be and where the computer knows it wants to play. And it drops the chip into the hole, and it breaks one of these 7 sensors. It breaks the beam, and then it'll know whether it's the computer or the human that played that chip, and stores it in an array. So we had to come up with a Gantt chart to help organize our start to end on this project. And there was a few milestones that we had to reach. I needed to understand the design before I did anything. Then I needed to design it and make sure that the magazine did what I wanted it to do. It needs to actually hold the chips and be able to release them. And that has been met. And then for my firing mechanism, I needed to get it to simulate properly on SOLIDWORKS before I decided to print it out. And then I needed to write code to make sure that it did its full rotation to actually release the chips.
And my milestones were choosing a sensor pretty early on the project. I got that one done pretty easily. I had to choose. I was caught between 2 of them, but one of them didn't have data sheets, so went with the one I did. And then I wanted to get store an array, which I've done. And then the detection does work. So like when it's played, it does detect via interrupts. And then my last goal is to get it all working together, and the chip storing in the array would all summon across when you play it. And I haven't got that one yet. I'm pretty close to that.
All right. My portion right here, my first milestone is just, again, like Eric's, completing design, understanding how everything's going to go together, having a full assembly in SOLIDWORKS so that I'm not constantly reprinting parts. Did a few times, but not as many as I would have. And then after that, it's actually printing the individual parts and getting those in the physical form. You know, the gear, the gate itself, the track for the gate, the mounting systems, and all that printed out. And then another milestone after that would be the assembly of all this coming together. And then the last milestone for this section would be the code for running the motor to get to the 7 positions to play and the 8th position for the human to play completely out of the way. It's the last milestone for me.
This is my initial magazine design. I was gonna use like some kind of linear actuator to push a chip straight out, and I decided to change that pretty quickly. So I figured that, well, this design would work a little bit better. So this is my magazine. It holds up to 21 chips, which is the maximum amount of turns that you can have in Connect 4. The chips will automatically fall just because gravity pushes stuff down. There's an opening here to allow my sweeping mechanism to go through to push the chips out, and they fall vertically into the board. How I got the 6 inches is I multiplied the chip height by 21 chips, and that'll hold all of them. The inside diameter of the magazine is just a little bit larger than the diameter of the chip. And this is just big enough to allow the sweeper arm to go through, but it's actually smaller than a chip, so they won't fall out the side. It's also bigger in the front too. Well, my sweeping mechanism consists of a 5-volt stepper motor that has 2,024 steps, and then there's 4 steps to, or 4 like poles in the motor. So you need to do 506 activations of each pole to get 1 full rotation, and a little time delay in the code to get it to actually activate the proper ones at the proper times. The sweeper itself, this little arm is 2.5 inches long, so that gives us a pretty good sweeping radius through the magazine, and it's, you know, thin and wide enough just to be sturdy and actually push a chip no problem. And this little piece right here, that where it mounts, there's a little hole cut into it to mount to the stepper motor, and that's a real tight fit, and it works perfect. This is the code that I use to move the motor. You can see it's got a for loop here where it counts to 506, and this is the first coil or pole activation, and here's the delay, and then it goes to the next one, and then delays and comes back and does it again. It's 506 times, get 1 full rotation.
My turn. All right, so this is my original sketch, just with some labels added to it. For my original design, that hasn't changed too much. There's a slight change in how I'm actually receiving the chip from Eric's mechanism. It was going to come down from the end and roll in, but now we're going to have it just drop from the side and roll down. We'll see that in the diagram later on. Next slide, please. So I'm just to try to avoid some confusion, I'm just building up the pieces here. So first, this is just that motor Eric was talking about, and with the mount, it's where it's going to be mounted to the game board to hold it in the proper position. The gear that will go on to the drive shaft of it, and then this is the actual gate. This is the hole where the chip will fall through, and this is a rack and pinion mechanism to move that position back and forth. And then here it is in the actual track. These 2 posts right here go into the vertical portion of the post where the actual leg for the game board would be. And then it's at an angle, so when a chip falls at the end, it will just roll down until it hits the opening or the backstop and fall down through the opening wherever it is positioned. Just a rough dimension there. It's approximately 12 inches end to end. And then this is the vertical view. You can see all the openings looking down.
So just initially how I was planning on mounting it was I was gonna just go on the front of the board and have some around all the sensors on it, but then eventually our design of the entire, like the top system, once I figured out how that was gonna be, I decided to mount stuff on the top and have the sensors hang down in front of the holes, which would work better with theirs. And then, you're good, you're good.
You're building off of
Yeah.
our design as well.
Yeah.
No.
And these were the brake beam sensors I chose. They have this is the emitter and this is the receiver. It operates at 20 million. I'm running it at 20 milliamps. Pretty much what happens is the chip falls through and breaks the beam, which is going to trigger an interrupt on the rising edge, and then it'll slow the chip in the array. And this is I have to pick out a board. So each of these have to be 1.3 inches apart. So I have to have a bunch of different boards, and I have to calculate it accordingly. They all need all the boards are going to need resistors. This is just my schematic here. And then this is my code. I'm gonna switch these to a 2-dimensional array. So pretty much how it works is if the play, so this is determining who's playing first. So the if it's 1, then the human's playing first. If it's a 2, the computer's playing first, and then I have a chip place variable that when the interrupt triggers, it's gonna tell where in the system that the chip is, and then it's just gonna store a 1. Add this order count goes to cycles between 0 and 1. If it's a 0, then that means the human went, and if it's 2, that means the computer's going. And then in my actual code, it's going to be locked, and then in the interrupt, when the chip breaks the line, the D is going to be set to 1, so it can actually go into the array store code, and then once it's done with the D is 0. And yeah.
I just want to mention one thing I forgot. In my section for my stepper mode, it's going to be using the same code that Eric has, just a different number of steps for all 8 positions it's going to be traveling to. It's going to be the same thing, just change that one number based on the location it's going to travel to. Okay, so then this is our final product, the assembly for everything together, minus the sensors, because that's not really something we're going to print out. We'll probably have a cut a piece of wood. It'll be a little bit easier. We don't need to print out something to glue the circuit boards onto. As Andre said at the beginning, wood's a beautiful material, and we should be using that. It's easy to work with. And one part that we didn't see in one of the previous schematics is this right here. This is open, just so you can see it. There'll be a shield for it to ensure that it doesn't just fall out onto the ground. It'll actually fall into this channel here, this track, so that once it falls, it'll just roll until it reaches its final destination and fall through. Everything put together. And then one thing, we didn't have a slide for this here, we just forgot, is more of the play code. I mentioned it earlier, but we're playing in order, we're scanning for all the positions, the array we've stored, just looking in the array for if the human is 1, if there's 4 in a row, the machine knows it's lost, it knows not to play, game's over. Light up a lost light or a win light, possibly. And then it's looking for options to play for 3, looking for options to block for 3, and it's doing this by scanning the rows horizontally, vertically, diagonal, and not in particular order, but looking for 3 in a row. And then it has to go through statements. Is there a playable space on either end of that 3 in a row? Is there a chip underneath that? Is the opening open? And then if so, if all those conditions are met, it'll play a chip there and win. And then obviously it'll be doing the same thing for a human, just trying to block. And then if there's no case like that, it'll look for 2 in a row. And if there's 1 in a row, it'll just try to play next to it to get 2 in a row. Anything else you guys want to say?
We've mentioned how it's like we're mounting it to the top. You can detach and reattach our system.
Yeah, there's only one point of contact for it. So just these
It'll
two
pop
posts,
out and pop back in.
drop it in, and then.
So it's more of an add-on than an actual.
One thing is it could make it slightly top heavy. We might have to make sure the feet are secured, either with an adhesive or screw the feet into a board just to ensure that it doesn't fall over during gameplay.
So you don't actually have all the pieces glued together, because are you reprinting that long piece?
I just printed it today because I couldn't until the machine
Right,
was
okay.
fixed
So
yesterday. So.
you don't, I think you're right, it's gonna be top heavy, so do you have a plan for?
Yeah, so I'll just have to take a piece of plywood, maybe nothing too large, and position the feet, and then have the feet screwed into place, and then you just put the board on top. And just put away the bottom, basically.
So, you got a lot of good SolidWorks pictures, except you got like no labels on it. So this is like front view, back view, is that correct? What I'm seeing here?
Yes, yep, this is.
Okay. Is there some reason why the ramp is horizontal and the board is tilted?
It's so that the chip will actually roll down, because if the chip's dropped and the ramp is just horizontal.
You're
it'll-
missing the answer.
Not on the picture.
The way it's shown there, you're tilting the board.
Oh.
It's because
And
when
the
we
chip
built
can't
it,
roll.
it was just, it was built on that, see the plane? That's the horizontal plane.
It just didn't.
And that's just. it just-
Okay, so that's an oversight on your part. That should be tilted, right? The board should be horizontal
Yeah.
or
yes.
vertical,
Yes.
and the whole ramp system tilted. Okay, so that's a minor detail. I'm going to assume that was the case, but it would be nice if it looked like the way it should look. If you go back a couple to the sensor schematic. Okay, so you've got this schematic.
Yeah, it's
How does
the
it-
same for both the emitters and the receivers, because the emitters need a current limiting resistor and the receivers need a pull resistor.
Okay, so there's got to be a difference between them though, right?
No, this circuit's
Same
actually-
resistors?
No, I'm going to use 10K for pull-up and 300,
Okay.
like 220 for the current limiting.
Okay, so why are those boards looking different to me?
Oh, because I think I mentioned that. The holes are 1.3 inches apart, so I need to have these sensors. So the sensor is 1.3 inches apart on the board, so when I pull them down, they'll go actually cover the holes. And I couldn't all print it out on one board, so I had,
Oh, okay.
so I had to split it all up and had to make measurements so that actually they would line up.
Okay, so there's gonna be like one of the lower board and two of the upper, or?
There's going to be one of this, and then there's actually another board that has. I guess I probably should have put it there, but there's another one that go after this one that's the same size as this one.
All right.
Because there's 7
and
sensors.
I think,
2, 2, and 3.
this is a style issue more than anything, so if you had doubled it up, if you had shown another copy of that,
Yeah.
it still wouldn't be.
Yeah, it's not the same exact one as that. They're shifted over a little bit for a while.
Okay, but in terms of you presenting this, wouldn't it make more sense to put them along the bottom of the slide?
Yeah.
And put them in order?
Yeah.
And then say the Connect 4 board lines up with this or something?
Yeah.
But just in terms of you trying to convey that
Yeah.
idea that it's
Yeah.
3 boards dovetail together,
Yeah.
that would just be a nicer way to demonstrate, to present that, so. Okay. I think your array code, I think it's fine. I think you started with an apology or
Oh, wrong
something
way.
that you wanted to, you meant to change something.
Yeah. I had 7 arrays because when I was doing this, I
Yeah.
never wrote a 2-dimensional array. I completely
Just
forgot about it.
in general, if you're standing in front of a crowd, don't start with, "This is wrong."
Oh.
Yeah.
I mean, it's not wrong. It works. I was just
Yeah,
gonna
so
change
you can
it.
say this is an early version of it that only
Okay.
represents one column or so, something like that.
Yeah.
So that's just, again, a presentation style thing. But this would have worked a lot better if you had a little flow chart standing. You got all that white space or purple space over to the side, not being used for anything. I can almost read the text, so the text is big enough, but you can't look at that and know what you're thinking. A flow chart, a part of a flow chart, a state diagram, something graphical that draws your attention first and lets you talk about it would be a really handy thing. And just keep working back. So like on this one, you got a few things labeled. I actually like the use of the arrows, but I'm a little bit confused by that diagonal arrow, white arrow against the red.
This is part of the chip path here. So
Yeah, and then, but then you're showing this big, massive arrow coming down, like the chip is falling straight down.
Mhm.
So, I mean, it's just a little thing, just make an L-shaped arrow or something.
Okay.
You know, just connect it up. And where's the chip coming from?
Starting this arrow right here. We'll jump right
Okay,
here.
so
I can probably add a chip there.
Yeah, add a chip there, or do a dotted outline of the magazine mechanism dropping a chip or something, just to,
Mhm.
right, so the arrows are, it's good to use the arrows, but you use them in a way that's confusing, I think,
Okay.
to me at least. And also the 12-inch thing, you're showing the dimension, which is great, but you're using the same style of arrow.
Mhm.
Right, and so that style of arrow is attempting to show motion, and then you're using motion arrow again, you know, so it's a minor detail, but it's just like, you can use different arrow styles to indicate different things, so. Otherwise, it's a nice, I like the color differences.
Yeah.
You get a sense there are different parts there, and
I was actually having trouble. I know you may have mentioned before presentations, like make sure you can understand any diagrams.
Yeah.
When
So-
it's all gray, you're just meshed together.
yeah, that's a huge problem. The fact that you label the chip path is good, but the title of the slide is the slide gate,
Mhm.
and you didn't label it.
Oh, okay. Well, that's, I guess that was the whole assembly.
Yeah, no, I mean, I think the things you were saying during it made sense. I know you know what it does,
Yep.
but for someone walking in and seeing this for the first time, a label pointing to the green part from slide gate down, it would be
Okay.
huge, right? And that's in motion, and the thing is, the slide gate moves when the motor rotates, right? So
Yep.
you could have some more arrows showing that.
On the previous
And then the
slide.
chip rolls down, it's really, yeah.
Arrows here.
Yeah, that's not bad. Again, you got the title slide gate, and you're showing 3 different parts, right?
Okay. Yeah.
So-
So I guess that's just my terminology. I was calling my whole section, the whole assembly. I was calling
Yeah.
it the slide gate, and I was just trying to avoid confusing by building up. Just showing the base, just the motor, and
Yeah,
showing
just label it
different
the
parts.
base.
Just
Label it what you said it was. That's all I'm saying. They're pretty pictures, but left alone, without your script, nobody knows what
Okay.
those pictures mean. So, and you could correct that with just a couple labels. So I think that would go there. Label the pinion, label the slide as the rack. So, yeah, I think we're good. I like the fact that Eric, when he was talking about his magazine, started with the diameter of the chip, and worked from there. I think you got off track with the sweeping mechanism. The number of poles of the stepper motor and all that is significant for the software, but you don't want to get lost in that. I forget exactly what you said. I just kind of circled it. You said something weird there.
Yeah, I said something weird, and then I said, this is what I was talking about.
Yeah, and
That's
then
what I
you
did.
kind of brought it back here. So there was some significance there, but it's not a huge
Okay.
thing. But I do want to ask you, why did you pick the 2.5-inch long sweeper?
I liked the radius of the path that it would take.
Okay.
That's why.
All right. So did you actually?
Well,
When
okay,
you say
so
you liked it.
I didn't want it to be like crazy long and stick way off the board
Okay.
and stuff. So
Yeah.
I wanted to get it as small as possible.
Okay.
But I
So what's the
also-
smallest it could be? Is there a range of acceptable values? Like it could be anything from 2 to 3.5 inches, and you just pick 2.5 in the middle, or how would you?
Yeah, I did do a little range that I could go between. I think I said like, what did I say? 2 to 3 inches is what I went with. So I wanted to keep it small, but I needed it large enough to actually sweep through the magazine.
Okay.
So,
So did you do like a motion study in SolidWorks?
I did. That's what I
Okay,
did.
so
I
that,
did a-
and you tried different lengths? I mean, if that's what you did, that's fine. If you did something else, that's fine too. I mean, you could imagine doing some geometry calculation, right? You're gonna sweep 90
well,
degrees.
I guess I did a mental
Okay.
geometry
So
calculation.
when
I
you-
didn't actually.
Let's say you're talking about the satellite you're going to build for NASA, and you stand up in the presentation and say,
Yes.
I like this number, so that's what I used. Is it going to give you any credibility? I don't think so. But if you
That's the
start
first time.
with, we had a park, it was this diameter, and we needed to sweep through it and make sure we catch the chip, and it could be any number from here to here, and I picked this number in the middle, there's a little bit of rationale there, right?
Okay, so I should have said
So-
that definitely had to be over.
You're pointing
inch
at
and a
that. We
half.
did this before. You need to walk over there and show us where you're
Oh,
pointing.
so I guess the 1.5 inch diameter is probably what I should have said. It definitely had to be over that number.
Yeah. And what would have been really useful to do is do an overhead view, looking down at that chamber with the 1.5 inch mentioned, and show where you're going to mount the motor, so everybody in the room could understand you've got an 1.5 inch there plus the offset for the motor, right? That's what you're doing in your head.
Mhm.
You're adding those numbers up, and it needs to be a way to show that, and not say, I like this number. I like 1,000 ohms, but every once in a while I have to do an Ohm's law calculation to prove that 1,000 ohms would work, right, in my circuit. So, any other questions for people?
David had one.
Yeah.
I had a question about the code for that.
Stepper code?
Yeah. Are you actually gonna have the delay at 200 milliseconds at the bottom? Because if it's doing 500 steps, you're delaying.
It only takes
Oh,
about.
it's just delaying there. I see it. The other question was. I answered that question.
You answered
The other
your own
question is,
okay.
are you gonna be able to? I mean, it probably only takes a quarter turn or something, half a
No, I'm
turn.
doing a full rotation.
Right, but it only takes
Oh,
a certain amount to
Yeah.
kick the
Yeah.
It'll actually it'll
chip
play
out.
sooner before, you know.
It'll play before it's
Yeah,
done rotating.
Yeah, exactly. So that'll kind of speed up the time as well.
yeah. So basically, I guess your answer is 3/4 of the rotation is happening in background. Like it
Gotcha.
doesn't need. It's not even part of the game.
Gotcha.
It just kind of resets back to the position ready to fire the next one.
So will you set the slide gate before it
Yep.
moves out?
Yeah, it moves position, then drops. Just to be sure.
Once his slide gate moves to where we want it, then it will set a signal, which right now I have just a push button, but that's going to change to the signal that says that Harry's code is done.
Yep.
Why the B team?
Because
That's the grade we're going for.
No, when we were picking the team at the very beginning, that was Team B, so very creative.
All right. All set. Thank you.